In this part of the lecture, we're going to continue investigating how pressure works in fluids. And the next thing that we're going to look at is something called Pascal's principle. Pascal's principle says that a change in pressure at any point in an enclosed fluid at rest is transmitted undiminished to all points in the fluid. That sounds maybe a little bit confusing, so let's talk about what that actually means. So here in the figure you can see I've got this U-shaped tube which is filled with the fluid, and there's a piston here, and there's another piston on the other side of the U, and I'm going to push down with some force, and that's going to create a pressure in the fluid because the force is going to be distributed across the area of the piston face, and that's going to create a downward pressure. Now, that pressure that's created right here gets transmitted at every point in the fluid, so that on the other side of the U-shaped tube, that same pressure gets transmitted all through the fluid, and you'll see an upward pressure on this guy, which will lift it up. So we have a force here, which creates an increase in pressure that gets transmitted through the whole fluid all the way to the other side, which will lift this guy up. Now, if you were swimming down here and then this force were applied, you'd actually feel the increase in pressure right there because it's everywhere in the fluid that you feel that change in pressure. Now, the great thing about Pascal's principle is that you can manipulate it to create a mechanical advantage. We talked about simple machines previously, how you can input a force and that the force can be increased by this simple machine. Now, what's the downside? The downside was that the force would be applied over a smaller distance. And if you remember, we had this basic idea that the work, the force times the distance, that is what could not change. But I could, through a simple machine, increase the force and decrease the distance, or vice versa, as long as when you multiply them together, you get the same number. The same basic idea is applied here. What I can do is I can have 10 kilograms on this piston, and that's going to create a pressure all through this area. Now what happens is that pressure gets transmitted to every point in the fluid. Now when you come over here, we have a much larger surface, and so this worth is going to give me increased pressure because of this 10 kilogram weight pushing down on this area. And so this amount of area is going to have the force of that 10 kilograms weight pushing down on that area. Well, that pressure, force per area, is going to be transmitted over here. So here I've got an area that's going to have 10 kilograms worth of weight pushing up there, and then 10 kilograms on that area and that area, because the pressure is the same all through the fluid. And so by simply extending the area, you create much more force distributed. And so this 10 kilogram mass here can actually support 500 kilograms. And the way that you do that is you have the area here and 50 times the area there. And those would, of course, balance out. Now, what if you had 400 kilograms here and 10 kilograms there? Then you would actually have enough pressure to lift this guy up. And so this guy would sink down a little bit, and this guy would be lifted up. Now, what's the distinction? This guy would go down a certain distance. This guy would go up, but it would go up 1/50th of the distance. And so, again, you get this force increase, but what you lose is the distance. And so this is, of course, we call this hydraulic principle, and we can see an application of this in the rack that lifts your car up at the service station, so the mechanic can get underneath the car and, change the oil or, service the car from underneath. And basically what you have is you have this reservoir of oil here and an air compressor. And so you turn on the air compressor and it pushes air in here, which creates a downward pressure on the oil. which is then sent through this tube to over here, to this, and over on this side there's a piston. And so the pressure that is put here gets basically reversed. So in this case, you have this guy go down and this guy goes up, and it lifts the car. So basically, you have the air compressor is putting extra pressure here, and that's creating a force per unit area over this large area, and that pressure is going to be transmitted over here to this piston, and that's going to be the same force per unit area. Now that force per unit area is acting now on a smaller area, so that means the force is getting magnified. And so for not a very strong force or air pressure over here, you can get tremendous lifting force on the other side, enough to lift a car up so that you can get underneath it and change the oil. So let's check our understanding with our checkpoint here. So the first question says, as the automobile in the figure is being lifted, how does the change in oil level in the reservoir, that's this part here, compare to the distance the automobile moves? And basically, the oil level drops just a little bit, and it creates a much bigger rise of the piston, because the area of the piston is much smaller than the area on which the air compressor is acting, and that creates the effect. The next question is, if a friend commented that a hydraulic device is a common way of multiplying energy, what would you say? Well, hopefully you would say that that's not true. We know that work or energy is going to be force times distance, and that's not allowed to change. The work is going to be the same. But what can change is the force and the distance. And typically, you want the force to be bigger and the distance to be smaller. Although sometimes you want the backwards of that. You want the distance to be bigger and the force to be smaller, but usually you want the force to be multiplied. And this would be one of those applications. We need a bigger force to lift a very heavy car. The next topic we want to look at is buoyancy in gases. And so we've talked about buoyancy in liquids, Archimedes' principle. This applies in gases as well. It applies in any fluid. And remember, the basic idea is that when you're in a fluid, the deeper that you go, the more the pressure is. And so if you've got like a hot air balloon here, you have the pressure from the air pressure pushing down, but also pushing up. And the pressure from underneath, because there's more air above, the deeper you go, the higher the pressure. That means the pressure that is underneath is bigger than the pressure above, and that creates a lift. And so the hot air balloon will rise because of that buoyant force. Now, why don't all objects float like a hot air balloon? Well, it has to do with the volume taken up by the hot air balloon. It's pumped up with helium or hydrogen, or even just gas that's been heated up so that it's less dense, and it expands the balloon so that the buoyant force is strong enough to overcome the weight of the basket and whoever's in the basket. You are also being buoyed up by the air pressure, but you don't have enough volume in your body for that buoyant force to be as strong as your weight. Hence, you don't float. The next thing that we want to look at is called Bernoulli's principle. And this applies to when the fluid is moving. When we were talking about Pascal's principle, we were generally considering the fluid as being static. And of course, we had the idea that we might push it down and move it, but we weren't really concerned about the motion of the fluid itself, just that the pressure was being transmitted throughout it all. But here we're looking at what happens as the fluid itself is moving. And the basic rule is this: when the speed goes up, the pressure goes down. Over on the right, we have an example of how this can happen. So here we have a pipe, and the pipe necks down to a narrower pipe. And so what happens is that when the fluid flows into the narrower segment, the speed actually increases. And there's a relationship called the equation of continuity, which says that the product of the area and the velocity of the fluid is constant. In other words, this big area times this velocity has to be the same as this little area times that velocity. So since the area 2 is smaller, that means the velocity 2 has to go up. And what happens over here when the velocity goes up? Well, we have Bernoulli's principle that tells us that when the velocity goes up, the pressure goes down. And one way that we can depict this is through what are called streamlines. And so here we can see that I've got the fluid here going through this pipe where the neck is narrowed, and these lines represent motion of fluid down the pipe. And what happens is as they go into the narrower part of the pipe, they bunch together. And basically the rule is that when the streamlines are closer together, the velocity of the fluid is increased and the pressure is decreased. And this is how an airplane actually generates lift. As the airplane is moving, air flows over the wing. And the thing about the airplane that makes it work is the wing is shaped so that the air kind of bunches up on the top compared to the bottom. And so what that means is that you have the air is moving faster on the top side of the wing than it is underneath the wing. And that reduces the pressure above the wing, but the pressure below the wing is still stronger, and so that creates a lift on the wing. That's why airplanes don't work when they're standing still. If you're on the runway of the airport, you have to get the plane going forward so that the air will be rushing over the wings. That's necessary to create that lift. And it's all based on Bernoulli's principle. The faster the air goes, the lower the pressure. And so you design the shape of the wing so that as the air goes around the wing, on top, it goes a little bit faster than underneath. That decreases the pressure on top and increases the pressure below, and that creates lift, which lifts the airplane. That's also why, like in movies, you've seen like the engines on the airplane cut out, and the airplane, it coasts for a while, but eventually it'll crash if the plane doesn't have the engines restart. That's because you have to be going a certain velocity in order to create enough lift to counteract the weight of the plane. And if you're going too slow, you won't have enough lift. This idea of Bernoulli's principle also explains how a curveball works. When a pitcher throws a curveball, so when a pitcher throws a straight fastball, he doesn't or she doesn't want to put a lot of spin on the ball. So the ball is going through the air, and the streamlines go around it pretty symmetrically because the ball is just moving straight. But if you throw the ball in such a way that it's spinning as it goes towards home plate, the seams on the ball, they basically drag the air around the ball as the ball is spinning, and that causes the air to bunch up, and that creates a crowding of these streamlines, which again, what does that tell you? The velocity is up, the pressure is lower, and so the pressure on this side is higher, the pressure on this side is lower, and the ball will tend to curve. Here's another application of Bernoulli's principle. It's a demonstration that one can do. So we have these two toy boats that are in a tub, and they're being held in place by this string. And then what happens if you come and you send a stream of water in between the boats? What's going to happen? Well, the water in between the boats is going to be moving forward, and that's going to cause the pressure to drop, because as the velocity increases, the pressure decreases. And so you're going to have more pressure coming in from the sides than you have going in the middle. And that'll create a force that pushes the two boats together. And again, this is a result of Bernoulli's principle. which is a very important idea for understanding how fluids work when they're moving.